Okay, next problem is in 220 kilovolt system, the reactance and capacitance up to the location of circuit breaker is 8 ohms and 0.025 microfarad. Okay, so reactance and capacitance up to the location of the circuit breaker is given for a system of 220 kilovolts, that is 8 ohms of reactance and capacitance of 0.025 microfarad, and a resistance of 600 ohms is connected across the circuit breaker. So whenever a resistance is connected across the circuit breaker is mentioned in the problem, that means that it is resistance switching. So in this problem, you have to determine the natural frequency of oscillation, damped frequency of oscillation, critical value of resistance which will give no transient oscillation, the value of resistance which give no transient oscillation at 1/4 of the natural frequency of oscillation. Okay, so since reactance is given, we can determine the inductance. So we already know the formula XL equal to 2 pi FL, and from this formula L is equal to XL by 2 pi F. So XL value is 8 by 2 pi into F is 50 hertz according to Indian standards. So 8 by 2 pi into 50, you will get L as 0.0255 Henry. And natural frequency of transient oscillation formula is well known to you, 1 by 2 pi root LC. So L value is just now you have calculated 0.0255 and C value is 0.025 into 10 power minus 6. Substitute L and C value in this 1 by 2 pi root LC formula, you will get 6.3 kilohertz. So next you have to determine the damped frequency of oscillations. Formula for that is Fn dash is equal to 1 by 2 pi root 1 by LC minus 1 by 4 R square C square. So you already know the L value and C value. R is the resistance which is connected across the circuit breaker, that is 600 ohms. So substitute L, C and R values in this formula and you will get damped frequency of oscillations, that is 3.41 kilohertz. Okay. So now we have determined the natural frequency of oscillation, damped frequency of oscillation. Okay, next they have asked us to determine critical value of resistance which will give no transient oscillations. Okay, so you know different values of resistances. In resistance switching we have discussed for different value of resistances how the transient oscillations vary, at what condition transient oscillations will damp. At critical resistance transient oscillations will damp. No transient oscillations will be there at this critical value of resistance. The formula for that critical value of resistance for which transient oscillations will damp is R equal to 1 by 2 root L by C. You know L value and C value. Okay, so substitute in this formula R equal to 1 by 2 root L by C. You will get R as 504.6 kilo ohms. If you have completed type C, if you have not completed type NC, anybody can complete NC? Completed everyone? Okay, we'll proceed. Okay, no NC, isn't it? No NC. Nobody has typed NC, I'm changing. Okay, so they have asked to determine natural frequency, damped frequency and critical value of resistance, which will give no transient oscillations. We have determined it. Next, we have to determine value of resistance, which give no transient oscillations at 1/4 of the natural frequency of oscillation. So, let us assume that the resistance which will give no transient oscillations at 1/4 of the natural frequency of oscillation, that resistance value is R. Okay, let us assume some notation. Okay, so let us assume that resistance is R. Okay, so at that resistance, what about the frequency? The damped frequency is 1/4 of the natural frequency. Okay, damper frequency of oscillations is 1/4 of natural frequency. What is the natural frequency value? We have already calculated. Okay. So natural frequency value, it is 6.3 kilohertz. Okay, you can see on your screen. Natural frequency is 6.3 kilohertz. So now for determining this R value, the damped frequency of oscillation should be 1/4 of the natural frequency. So for you, slide has changed. For me, it didn't change. Okay. So 1/4 of natural. So 6.3 by 4. You will get 1.575 kilohertz. That is our damped frequency. Okay, for determining this R value. So Fn dash is equal to 1575 hertz. Okay. So now you already know the damped frequency of oscillations formula, that is 1 by 2 pi root 1 by LC minus 1 by 4 R square C square. So now this R is not the resistance which is mentioned in the question. Okay, this is the R which is to be connected across the breaker. Okay, which gives no transient oscillations at 1/4 of the natural frequency. Okay, so let us determine this resistance value. So just now you have determined the damped frequency value, that is at 1/4 of natural frequency, that is 1575 hertz. Okay, so you can substitute 1575 is equal to 1 by 2 pi root of 1 by, you know L value, you know C value, you don't know R value. You have to determine the R value at 1/4 of natural frequency. Okay, did you complete? If you are not completed, type NC. Okay, NC. Someone has typed NC, so I will wait. Whoever types NC, as soon as you complete, type C. I will remember your roll number. That's the reason. Okay. Okay, no one else? Okay, you can solve it on your own. Okay, you can solve it. I have told you what to do. Okay, so I have substituted all the values here. L value, C value. 4 into R square into C value. I have substituted, I have simplified it. I have got 521.5 ohms. So 521.5 ohms resistance will give no transient oscillations at 1/4 of the natural frequency of oscillation. If you complete, inform me. If you are not completed, type NC. If somebody types C, then only you type NC. Till nobody types anything, I will not change the slide. Okay. Someone has typed C. If anybody else who have not completed, you can type NC. Okay, then we will go to the next problem. Okay, for you slide has changed. For me it didn't change. Yeah, now it has changed. Okay, next problem. A circuit breaker interrupts the magnetizing current. Okay, circuit breaker is interrupting magnetizing current means what? It is a low current. Okay, so you must carefully read the questions whenever in this subject especially. Okay, so circuit breaker is interrupting magnetizing current means it is a low current. So it might be a transformer, a no loaded transformer winding or a shunt reactor connected to the circuit breaker. So whenever the circuit breaker has to interrupt the magnetizing currents, that is low inductive currents, what will happen? Current chopping will occur. Okay, so current chopping will occur means current will be interrupted before its natural current zero. Okay, all these things should come to your mind. Okay, so whenever you are reading the question. So a circuit breaker interrupts the magnetizing current of 100 megavolt ampere. Okay, transformer at 20 kilovolts. Okay, so it interrupts magnetizing current. Okay, for an 100 megavolt ampere transformer at 20 kilovolts, the magnetizing current is 5% of the full load current. Okay, and the current is suddenly interrupted. Okay, this inductive, low inductive current is suddenly interrupted at 53% of its peak value. Okay, and the stray capacitance is 2500 microfarad, and inductance is given, that is 30 Henry. You have to find the maximum voltage which may appear across the circuit breaker contacts. So due to current chopping, okay, uh, due to current chopping, the voltage, as soon as current chopping occurs, the voltage that appears across the circuit breaker contacts is known as prospective voltage. I hope you remember. Okay, prospective voltage will appear across the circuit breaker contacts. So now you have to determine that prospective voltage. Maximum voltage is nothing but here prospective voltage. So full load current of the transformer you can determine MVA by root 3 into kV. So this formula is also very much familiar to you people. It's not new to you. Okay. So MVA by root 3 into kV. So MVA value, you know, that is 100 and 100 megavolt ampere. Okay, so you can write it here 100 into 10 power 6 by root 3 into 20 into 10 power 3, 20K. Okay, so you'll get full load current of 262.44 amperes. Okay, so initially we have determined the full load current. Okay, so they have mentioned in the problem the current is suddenly, the magnetizing current is 5% of the full load current. You have determined the full load current now, so you can determine the magnetizing current. Why? Because magnetizing current is 5% of full load current. If you complete type C. If you are not complete, type NC. Okay, I will wait. Somebody typed NC. Okay, completed. Okay, I hope everybody has completed. Okay, now we have determined the full load current, and in the problem they have mentioned the current is suddenly, the magnetizing current is 5% of the full load current. Okay, so let us determine the magnetizing current. So it is 5% of full load current, 5% into 262.44, that is 0.05 into 262.44. You just multiply these two terms, you will get 34.44 amperes. So you have determined the low inductive current value, that is the magnetizing current, that is 34.44 amperes. Okay, so now one more thing that is mentioned here is the current is suddenly interrupted at 53% of its peak value. Okay, so this is our low inductive current. Okay, so its peak value, you can determine the peak value into root 3. You will get peak value of this magnetizing current multiplying with root 3, and instantaneous value of current at which is means that is 53%. Okay, current chopping has occurred. Okay, the current is suddenly interrupted at 53% of its peak value. Okay, current is interrupted at 53% of its peak value. So current at 53% of its peak value. So 53% means 0.53 into 34.44 root 3. Okay, just multiply it, you will get 25.83. Okay. What is the magnitude of current at the instant of interruption? You will get 25.83 amperes. Now, as soon as current is interrupted, okay, the current within the, means the arc current within the circuit breaker contacts is interrupted. What will happen? The energy stored in the inductor will be transferred to the capacitance, okay, or the capacitor. Okay, so the capacitance is charged now. So electromagnetic energy is shifted into the capacitor. So the electromagnetic energy is converted into electrostatic energy. So what is the electromagnetic energy? Half Li square, and electrostatic energy half CV square. So you know the L value, you know I value, just now you have determined. As soon as the current at which interruption takes place is 25.83, just now you have calculated, and that is equal to 1 by 2. C value, you already know, 25,000, okay, into 10 power minus 6, and V value you don't know. Okay, at what voltage, or at what voltage interruption, at what is the voltage at the instant of interruption. Okay, you know the current at which interruption takes place, but you don't know the voltage. So you can determine the V from this formula, equating the energy stored in the inductor and the capacitor. You can determine the voltage. This voltage is nothing but the prospective voltage that will appear across the circuit breaker contacts at the instant when current is interrupted. So the magnitude of current that is interrupted is 25.83. Okay. So if you complete type C or type NC, if anybody types C, if any other person who have not completed, type NC. Okay, so many of you have typed C, so I'm going to the next problem. Okay, so next problem is you have to determine the prospective voltage. What is the prospective voltage E across the stray capacitance of 0.0023 microfarad when the instantaneous current choked by circuit breaker is 7 amperes. The value of inductance in the circuit is 35.2 Henry. Okay, so you have to determine the prospective voltage. Stray capacitance is given. You know what is meant by stray capacitor. Where is the stray capacitor connected in the circuit, in the equivalent circuit? If you have attended my classes, you might be remembering. Okay, so capacitance value is given. Stray capacitance value, that is 0.0023 microfarad. Instantaneous current choked by the circuit breaker is given. Okay, that is 7 amperes. Inductance of the circuit is given. So each and every term is given. If you know the formula, that is more than enough. Okay, so prospective voltage is the voltage which will appear across the circuit breaker contacts as soon as current chopping occurs. Okay, so formula is E is equal to I into root L by C, or V equal to I into root L by C. In the problem they have mentioned specifically E term, that's why we are writing here E. So E is equal to I into root L by C. So I is 7, L is equal to 35.2, and C is 0.0023 into 10 power minus 6. Okay, it's a simple problem. Nothing much is asked here. Directly you can substitute and solve the problem. Did you complete? If you complete, type C. If you have not completed, type NC. So it's a very small problem. Directly you can solve it if it is given in your exam. Okay, next problem. For you it has changed. Not completed. Someone has typed not, they have not completed. Why? Okay, completed. Someone has, someone is still writing. Okay then, let's go to the next problem. So, in a short circuit test on a circuit breaker, the following readings were observed on a single frequency transient time, okay, to reach the peak recovery voltage. I hope you remember the concept single frequency transient and double frequency transient. Okay, so the test was performed on a circuit breaker short circuit test in a laboratory, and it is observed that a single frequency transient time to reach the peak recovery voltage is around 60 microseconds. Okay, so the time taken to reach the peak recovery voltage for a single frequency transient is 60 microseconds, and the peak restriking voltage is 200 kilovolts. So you have to determine the average rate of rise of restriking voltage and the frequency of oscillations. Okay, so this is the given formula. So you already know the formula for the peak average rate of rise of restriking voltage, that is peak restriking voltage by time to reach the peak value. So peak restriking voltage is directly given to you. Okay, so actually peak restriking voltage formula is 2V max. Okay, so here no need to determine the maximum value of voltage, no need to determine the peak restriking voltage also, because directly they have given in the problem peak restriking voltage value, that is 200 kilovolts. Okay, and time to reach this peak restriking voltage, okay, time taken by the transient to reach this peak restriking voltage is around peak value of this restriking voltage is actually, you already know the formula pi root L by C. Okay, so it is pi root L by C, but no need of using that formula also. Directly value is given, that is 60 microseconds. Okay, so whatever data is given, okay, you just substitute directly peak restriking voltage value and the time taken to reach the peak value, you just substitute in the formula. Okay, 200 into 10 power 3 by 60. Okay, so you will get 3333.33 kilovolts per microseconds. I think meanwhile I was talking, you might have already completed. I expect that. Did you complete? Okay. So average restriking rate of rise of restriking voltage you have determined. Natural frequency of oscillation formula is also very well known to you. Where is it? Yeah. So 1 by 2 pi root LC. Do you know LC? No LC is given in the problem. Okay. LC value is not given in the problem. But pi root LC is nothing but T max. Pi root LC is T max. What is T max? T max is the time taken to reach the peak value. Time taken to reach the peak value is nothing but our T max. So directly instead of pi root LC, you can write, I can add one more term here. So that it will be more clearer to you. Where am I? Okay, so this will be more clearer to you, then you will not confuse. Okay, so 1 by 2 into time to reach the peak value is nothing but pi root LC. So time taken to reach the peak value formula, you already know, that is 60 microseconds. Okay, so substitute this t value here, 1 by 2 into 60 into 10 power minus 6. Okay, you will get 8.33 kilohertz. Yeah, 8.33 kilohertz is the value for the frequency. Okay, so it's a very small problem. Only the thing is you must be able to write down the formula and you must be able to understand the question. If you are able to understand, you can easily solve it. Okay, so approximately we have solved 8 problems in this unit, and okay, so I will conclude here itself, and